Hi, my name is Borja Osejo. I'm a machine learning engineer at LinkedIn, and today I'll be presenting our work on promoting inactive members in an edge building marketplace. Let's start with some of the motivation behind this work. So in the real world, recommender systems will take the utilities or utility scores output by several different models and actually combine them to come up with a final ranking. So a lot of times you want to control for very specific business constraints and in an explicit manner, which can be fairly difficult when these models are machine learning based. That led us to believe that actually using a linear programming formulation for this problem would be critical because we could put these explicit constraints into the problem and optimize with those in mind. Now, we wanted it to be scalable, particularly because the online adjustment had to happen according to some very specific latency requirements. The specific recommender system we'll be looking at is the PYMK recommendation system at LinkedIn, or the people you may know recommendation system. And this system consists of individual rankers which optimize for different objectives or utilities, such as the probability of inviting someone to connect, the probability of accepting said invitation from another user, and other downstream utilities. And you can think of the objective function as some kind of combination of these models, which may be machine learning based. And with m models and n settings for each parameter, the grid search runs over m-1 by n configurations. The business consideration we wanted to take into account is this idea of incentivizing infrequent member activity. So a significant fraction of LinkedIn users remain inactive for prolonged periods of time, and we believe if we incentivize them properly, these users may actually start engaging with the platform on a more regular basis. This is a problem that we see across networks, which is this idea of a rich get richer phenomenon, where the active users are heavily favored in the system, and therefore the infrequent member experience degrades. So our work identifies these members that actually should be given a boost in their current rankings, and in order to do so, we're willing to trade off certain drops in source metrics with the benefits to the destination metrics, where the source are people sending out invites, and the destination are those receiving invites. You can see the linear program to the PYMK problem on the right-hand side of this slide, and we set up this large-scale LP to actually do two things, right? The main goal is what it always has been, which is to maximize the expected score among all possible source-destination pairs, and what we refer to as the score is this mix of the different utility models that we've been talking about. And the second goal is for each of the infrequent members to receive a minimum number of invitations. And the logic here is that by incentivizing these infrequent members to make more meaningful connections, they'll continue to come back to the platform and actually engage and contribute content. Now, because this is a two-sided marketplace and we're matching millions of members, and each of those has a subset of possible connections, this works out to roughly a few billion parameters. What really enabled us to solve a problem of this scale was leveraging Dualib, which is an open source Spark-based linear program solver developed by LinkedIn engineers. Now, what this does is it takes your original LP formulation in standard form, actually adds a quadratic regularization term, and then dualizes the majority of the constraints in order to make it amenable to methods like accelerated gradient descent and LBFGS. You can find more details on this in the paper itself, on the Dualib repository on GitHub, or on the wiki. So how does the PYMK system actually work, right? So we take user interaction data and feed that into Dualib in order to actually get the duals for the infrequent members. We're able to just push these duals to our online feature store, and those duals are then used to derive the solution. Just depending on the duals is exactly what allows us to meet these latency requirements that we have strict limitations for. So what do we expect to happen, and what actually happened? There were two immediate effects that we thought we would see, and the first one is a drop in session or engagement metrics, simply because invitations that were going to frequent members in the past were now going to infrequent members. And the second immediate impact that we thought we would see is these infrequent members actually receiving more invitations because we were explicitly controlling for that. In the long term, we expected the infrequent members to accept more invitations and therefore engage with the platform at a more frequent basis. So what actually happened? As you can tell by this illustrative plot here, we actually did see that drop in session metrics, but over the long term it's actually stabilized. And in terms of invitations being received by this infrequent member groups, we can see that they clearly have received more. They have accepted more invitations, and there's higher retention and more active users in the long run. So what's the novelty of our work? So this is the first paper to really apply linear programming to real industry data at such a large scale without adding any significant burden to the backend system. Now, generating a robust solution did require a lot of experimentation, But overall, the solution is stable and fault-tolerant, and at the same time improving the member experience. The LP formulation itself is actually now being extended to other use cases of LinkedIn, and it has actually kicked off a bunch of research and product development within the company.